Thank you for joining us for today's webinar, the TRB webinar on saving lives in autonomous truck-mounted attenuator systems. I'm Deanna Sparger with the Transportation Research Board. TRB will provide 1.5 professional development hours through RCEP to professional engineers who attend the entire webinar session. The email address you use to register must match the address you use to register an RCEP system. You must attend the entire webinar to be eligible for PDH credits, and the Q&A counts as part of the session. You'll see those credits in RCEP by the end of the week. Please contact TRB with any questions about receiving PDHs. At the end of today's webinar, you'll be able to leverage automated vehicle technology to reduce DOT worker fatalities while performing infrastructure maintenance. 2, deploy an ATMA program. And 3, operate new lead follower autonomous vehicle systems. As an attendee, you are automatically muted when you join the webinar. However, you may ask questions by using the control panel, which should appear on the right-hand side of your screen. The questions that you type in are not visible to the other attendees, but are sent directly to TRB and the moderator. Please type in any questions you have about troubleshooting software or audio, as well as questions about the presentations here. Please type in your questions at any time. After all presentations, our moderator will read the questions out loud. After the webinar, you will receive a follow-up email containing a link to the recording of today's sessions and another link to the slides. Now I'd like to introduce today's moderator. Our moderator today is Dr. XB Hu, he is an assistant professor at Pennsylvania State University in the Department of Civil and Environmental Engineering. Prior to joining PSU, he was an assistant professor at Missouri University of Science and Technology. His group has been pioneering the lead follower ATMA for transportation infrastructure maintenance and has published several journal articles on this topic. He is the committee research coordinator of TRB's AKR 10 Committee on the Maintenance and Operations Management. XB, I will now turn this over to you.
Thank you, Deanna. Hello, everyone. Again, welcome to the TRB webinar, Saving Lives with Autonomous Truck-Mounted Attenuator Systems. This webinar is jointly sponsored by AKR 10, Committee on Maintenance and Operation Management, and ACP 30, Committee on Vehicle Highway Automation. So today we have 3 presentations with presenters from public sector, private sector, and academia respectively. Our first presenter is Ms. Ashley Nyland, who is Assistant Director of Mobility Technology at the Colorado Department of Transportation. And she is leading the TPF 5380 Autonomous Maintenance Technology Pool Fund, together with Federal Highway and 14 state DOTs. Prior to this, Ashley served as the Director of Automated Driving System Research at the National Advanced Driving Simulator at the University of Iowa, where she also received her bachelor and master degrees. Our second presenter is Mr. Maynard Factor, who is the Vice President of Business Development for the Kratos Defense and Security Solution Unmanned System Division. He is responsible for the generation of new business development opportunities, worldwide sales and marketing, and he provides technical directions for long-range strategic planning, including the development of new products, capabilities, and internal research and development endeavors. Maynard offers an extensive background in the driverless vehicle capabilities, ground robotics, and unmanned system technology. Mr. Factor holds a bachelor degree in electronic engineering from the University of Florida and a master degree of business administration from the University of West Florida. Our third presentation today is Ms. Qing Tan, who is a PhD student in transportation engineering at Pennsylvania State University. And she is also the manager of a Smart Mobility Lab. Her research focuses on the testing, operation, and operational design domain of autonomous vehicles. She is a pioneer researcher on the lead follower ATMA vehicle system, and she was a recipient of Leo P. Russell Graduate Research Fellowship at Penn State, Ozark Chapter ICE Student Excellence Scholarship, and she is also the first place winner of Central Missouri ITE Student Poster Competition. She was the vice president of the ITE at the Missouri University of Science and Technology. So without further ado, let's welcome Ashley Nyland for the first presentation. Ashley, you can take it away.
All right, good afternoon. Are you able to see my slides, XB?
Yes, Ashley.
Great, thank you. Thank you, XB, and certainly for the TRB for having us here today. I'm excited to be alongside the other panelists. I'm going to open up today's discussion with an introduction to CDOT's program with our Autonomous Truck-Mounted Attenuator program. I'll speak a little bit to our program overview and goals, what deployment has looked like in Colorado, and I will also touch on some of the activities that we are doing in Colorado, and particularly with the Autonomous Maintenance Technology Pooled Fund. And I will leave time for question and discussion at the end of the webinar, and I believe XB is collecting those questions. All right, so for those of you that are not familiar with a truck-mounted attenuator in a Department of Transportation operation, we leverage it for following our slow-moving vehicle operations. As many of you know, we have a number of slow-moving maintenance operations in our department. We operate on, of course, the highway where there's very high volume speedway or high volume and high speeds. So to protect our maintenance workers, we have a vehicle that is following that slow-moving vehicle known as the attenuator. So in CDOT's use case, we're leveraging the autonomous truck-mounted attenuator to follow our paint striping operation. To adequately apply paint onto the roadway, we do need to be operating about 7 to 10 miles an hour. And in some roadways, we need to actually operate a bit slower. In our scenario, our men are actually sitting in that paint truck, which is the lead vehicle. They're sitting in that back area known as the doghouse. So if we did not have that follow vehicle, and an unsuspecting motorist came upon that vehicle, our men and women working in that doghouse area would be sort of in significant danger. So that's why we have the attenuator vehicle following that paint striping vehicle. But as you can imagine, in today's environment, that means that a human operator needs to be in that attenuator vehicle. So in the vehicle that is designed to be struck, we have a man or woman getting up every day to sit in that vehicle. So in terms of the goals for the Colorado Department of Transportation, why did we pursue this? Well, first and foremost, it is for our employee to protect our driver and remove them from that vehicle that is designed to be struck. We have a few other goals that we are leveraging our ATMA program for, which is, of course, to decrease that risk of operations. So just decreasing the opportunity, if you will, that our maintenance transportation worker is in that attenuator. We're looking at ways that we can increase efficiency to our operations, and of course, pursuing cutting edge technology, really leveraging technology to help improve safety for our operation. So just speaking to what the program has looked like at Colorado over the last few years, I'll go ahead and start that we did commence this program back in 2018. We had initial development of establishing the program definition, understanding the goals. Our initial goals were very simple goals, which is something that I cannot articulate the importance of enough, which were focused around installation of the technology, evaluating the technology, getting into operational status, which CDOT has been in, and I'll touch on a little bit later, versatility of the technology, and then finally statewide expansion. So from about 2018 to early of 2020, I should say, we were in what was known as phase one. So phase one focused on procuring the vehicle, establishing our programmatic approach to the vehicle, getting authorization to operate on the roadway, and then finally doing deployment. Phase two, which is 2020 to 2021, that's where we did expansion of our operation to higher volume roadways. We've actually added a second ATMA in our operation, and then also continue evaluation. One other element that I will highlight for CDOT's programmatic approach is that this is very much an interdisciplinary program that we have at the Colorado Department of Transportation. So this program features a few of our different divisions at headquarters and in our regions. So most notably, of course, we have the Division of Operation or Maintenance and Operations that is sort of the lead sponsor of the program. We work with our regions where this ATMA is actually deployed. And then there's other support from divisions like mine and the Office of Innovative Mobility and other divisions throughout CDOT. So it's very much a team department-wide effort. Very quick overview of the system and the technology itself. So as I alluded to earlier, we're leveraging a leader-follower technology. So in this scenario on here, you're seeing the lead truck is following that, and for us, it's following the paint striping vehicle. The idea is that the vehicles are retrofitted. So we're taking our production maintenance vehicles and they are retrofitted with the appropriate technology that allows for that leader follower. So there's a number of obstacle detection, radar, etc. There's of course the software system, computer system that's picking up the breadcrumbs that our lead vehicle is dropping, and that follow vehicle is mimicking the path of the lead vehicle. Of course, like I said, there's obstacle detection in there so that if something would come in between the two vehicles, there's intelligence to stop that follow vehicle. There's also a human interface that the safety operator leverages to operate that follow vehicle. In our scenario, our safety operator is, of course, in the lead truck. They have the opportunity to be either in the doghouse or in the front cab where the paint striper is at. And they're overseeing full operation of that follow vehicle. There's also vehicle-to-vehicle communication that is on top of all of this, so this technology suite, if you will. And all of these different elements account for redundancy in the overall operation and safety of the performance of the vehicle. So what does this look like for a DOT to get one of these on road? So here in Colorado, of course, there is a significant amount of procurement that has to be done and the installation of the technology onto those production vehicles. Then after we got through all of that, really the fun begins, as I like to say. So CDOT led a validation and acceptance test on a closed course setting that allowed us to test out all aspects of the performance of the vehicle. So really we had 15 different scenarios that were ensuring that the vehicle is operating as we would expect per the ODD and per the specifications determined in the technology. So things like the follow distance, the gap setting, the speed, obstacle detection, all of those different things were tested in our validation tests. And so you're seeing on screen here one of the testing scenarios. This is scenario 1, where the safety operator is using the user interface to remotely set that follow distance of the lead vehicle. And what we will do in one of those scenarios is that we will collect the data of the actual gap distance, or the distance setting, I should say, verify that both on the field and then also with what the automated driving system is telling us. We compile all of these results and then we assess, is it performing, is the system performing within the ODD that we expect and the limitations and the specifications in the technology suite. So again, here you're seeing our 2021 validation test. This was from our second autonomous truck-mounted attenuator that we deployed in the state of Colorado. So I should clarify, we do have 2 operational. The first one was in sort of our northern region of Colorado, and then last April we deployed the second one in our southwestern portion of the state. Again, here you're seeing another scenario from our validation test. This is a report that we furnished after all 15 tests were done. You're seeing the stopping distance that we both measured on the road, and then the status of the engine, of course, as expected in this test, that the engine would actually stop. And if you have interest in this report, please follow up with me afterward, and we are happy to share this. And just another test result to share, something that we like to always showcase is the test result from 2018, and we of course have similar results for 2020 and 2021. But this is illustrating the gap control of the human driver versus that automated driving system. So if you look here, you see the stability that's offered by that automated driving system in comparison with the human driver. Operational deployment. So what does this look like for Colorado? As I said, we've been operational since 2018, so we're going into our 4th year here. We originally started on the lowest volume roadways in Colorado. So those were roadways of average annual daily traffic of about 2,500 traffic or less. And then in 2020, we actually increased that after having a successful initial pilot deployment and initial success with our crews. We actually requested to our task force here in Colorado that approves deployment of these types of vehicles. We requested expansion to average annual daily traffic of 5,000. So that accounts for the roadways on this map that are blue, purple, and gray. And that comes out to about 27 individual state highways and then 41 individual roadway segments. Of course, that varies and changes as our roadway volumes change throughout the year and over the course of the years. One thing that we did this last year is knowing that we have had the ATMA program in our maintenance operations for several years, we saw the opportunity to really formalize our training for our operators. So what we did in about 2 months ago, actually, is that we formalize and standardize our ATMA training. So we have a formal maintenance academy here in Colorado, and we brought the ATMA training into that academy, and that's what we're working to do now. So in our new training, all of our operators participate in the validation test first and foremost. But what we did to formalize the training is that we have both a classroom component to our training and then an on-road component. So in the new training, we have about 2 hours of classroom time where they're getting introduced to the system. And then we go out on the road and we do a series of those scenarios that I featured earlier in the presentation here. And then after that, we tested their knowledge and see where there might be gaps in understanding. And really this is to, like I said, formalize the ATMA vehicle as one of our other maintenance vehicles in our operation. As XP alluded to, we also have a pooled fund that focuses on autonomous maintenance technology. We have about 14 members in that pooled fund to date. And that pooled fund is a collection of states that are all along the continuum of deployment for an autonomous maintenance vehicle. So we have 5 or 6 states that do have an ATMA in their program, but we have several other member states that are still finalizing their business case, looking at ways to integrate autonomous maintenance technology into their operations, and also really doing the planning to bring one of these vehicles. So this pooled fund focuses on research that can really facilitate and improve the performance of this technology. So if you're not involved in our AMT pooled fund, I would certainly welcome you to join one of our meetings. There's a lot of research that we've done through this group, and we continue to navigate challenges and operational deployment questions that come up, and really it sort of serves as that community of practice. A few research efforts that I'm highlighting that the pooled fund has tackled over the last few years. I won't go through all of these, but a few things that we've done is Colorado State University did evaluate some of the training that we had in the early days of Colorado's deployment, and we leveraged that research to actually improve our training materials and our training curriculum. We've had a number of research projects that focus on the deployment guidelines, documentation, how we can improve some of the documentation that we have around the ATMA and also standardize some of that. We recently did a tabletop exercise where we were evaluating if an incident happened on the roadway, what would be the response by the DOT and subsequently the other agencies that would be involved. So that included, do we have the appropriate standard operating procedures? Do we know how we would respond? What would all be entailed in there? And that was one of the really great research projects that came out. Other elements that we're featuring are cybersecurity. There's work zone data that's being investigated, and a number of other different things that's coming out of the work of the pooled fund. One other thing that the pooled fund is working on too is the development of a toolkit. And the idea for this toolkit is that it will allow a deployer that's interesting, or an infrastructure owner operator that's interested in deploying one of these in their operations, all of the information that we have collectively distilled together and and sort of work through together. It puts all of that into one document, if you will. So things like developing your business case, things like getting through the procurement process, understanding what procurement vehicles states have used, things like the specifications, and all of those sorts of things are in one sort of central piece. So again, happy to also share that with those that are interested. All right, a few lessons learned that I would like to highlight from Colorado's deployment. First of all, in the program initiation and sort of use case development is the importance of having an interdisciplinary approach. One thing that we found in the toolkit is that there are multiple divisions that are involved in any DOT. We see some commonalities in terms of the types of divisions that are involved, of course, with maintenance and operations, your fleet management group, perhaps the group in your DOT that's dedicated to connecting autonomous vehicles, research. So really thinking through an interdisciplinary approach is important. Of course, having that strong lead sponsor in your division is critical. And one thing that we see getting through procurement challenges of any public sector, there's always going to be some lags and hurdles that you'll have to get through with procurement. And so really understanding the importance and understanding what procurement looks like in your agency and what are the tools that you need to have, especially given that this is an innovative technology. One thing that we found in the toolkit was the importance of compiling quotes and different contracting vehicles and leveraging that for new procurements. A few other things is the program startup and operations. One thing that we found in Colorado is the importance of having a crew level sponsor, if you will, or a crew level champion. So someone at that transportation maintenance level worker that is really your champion to guide or to manage the vehicle, manage the technology deployment. When challenges happen, you have someone from that operator perspective that's really sort of that champion, really making sure there is that smooth deployment. Understanding that given that this is an innovative technological deployment, that challenges will arise, and navigating how to address those challenges while also being thoughtful with having a smooth operation on the roadway is something that we have continued to work through at CDOT. Of course, we did find there were a number of restrictions around COVID and how we could navigate those safely and successfully. And then finally, the importance of a seasoned startup. So here in Colorado, of course, we have 4 different seasons. And so thinking about how we need to start the season up and also shut the season down is something that we've worked away quite a bit. And I will leave you with just a quick video of our ATMA in operation last April.
Ashley, thank you for the great presentation. We will leave all the Q&A to the very end. Okay, maybe a few more seconds looking at the video. Okay, and Mena, if you're online, feel free to take over and start to share your screen. Yeah, we can see your screen, Mena.
Okay, are you seeing the?
You may have to
presenter
swap.
slide?
Yep.
There we go. All right, how we're looking?
Yep.
Good.
Yep.
Okay. Well, good. Thank you, everybody, for taking time to link up and learn a little bit more about the autonomous truck-mounted attenuator. My name is Maynard Factor, and I'm going to be talking a little bit about the technology and the system and how we ended up in the arena where we can deploy this, what's now considered really a critical safety system in the highway maintenance world. So just a little background. Oops, my apologies. So Kratos Defense, as the name implies, Kratos is a defense contractor. We have 6 primary areas in the defense industry that we do business. We do satellite communications, space and training and cybersecurity, microwave electronics, defense and rocket support services, turbine engine technologies, and C5 ISR systems. We also have an unmanned systems division, which is where I reside, and where the technology for driverless vehicles, unmanned aircraft, and other unmanned related products are developed. Overall, the organization has about 3,000 employees, and we do about $700 million in gross annual revenue. And we have about a 60-40 split between product development and services that we provide, defense-related services. We have over 60 locations worldwide, and our headquarters is located in San Diego, California. So giving a little more background on the Unmanned Systems Division, as I described, we develop very high-performance unmanned aerial aircraft. We design, develop, and field aerial target drones, which are designed to replicate real-world threats like cruise missiles, and they're used for training, for air-to-air defense training and weapons evaluation. We also have a line of unmanned tactical aircraft that are developed for a lot of different applications in the defense world that are needed, which we can't go too much involved, but you can see in some of the pictures there that they're pretty interesting looking aircraft. The technologies that we developed for the aircraft with our control systems, our navigation systems, has been leveraged into the driverless vehicle arena. We started developing driverless vehicles for the Department of Defense initially to be used as targets about 15 or so years ago. And these vehicles were vehicles of opportunity. They were vehicles that were provided by the military that we automate with retrofit kits and enable them to be driven remotely downrange, and essentially they're used as target practice and they get blown up. We started then expanding that product line to go into more tactical environments where autonomous technology could be used to reduce warfighter exposure to dangerous missions like route clearance missions or resupply missions. And so we developed a number of products there. The same sort of concept, the vehicles are provided to Kratos, and then we integrate retrofit kits to enable autonomous and driverless capabilities. We've automated a variety of types of vehicles, military type vehicles like Humvees and tanks. We've also done a number of cars, trucks, SUVs to serve for different applications in the defense world. And with the technology we developed for the military, we found an application where it could be leveraged into the commercial space, which is what we did here with the autonomous truck-mounted attenuator. If you think about the tactical application of the technology, where we're developing systems to reduce warfighter exposure to danger, here we had an application in the highway maintenance arena where we can increase worker safety, ultimately reduce worker exposure to danger in having to drive the TMA. And actually gave a great description of the TMA and its application. You know, essentially it's a shield, and it moves along with the mobile highway work zones when they're doing line painting or sweeping or patching or different maintenance applications. And the purpose of the vehicle is essentially to provide a level of protection for the workers and equipment ahead in the work zone. Somebody actually does have to get in this vehicle, and they do have to drive it. And essentially, while that person is in the vehicle, they are exposed to various dangers. I mean, the highway, the moving or mobile work zone is operating at usually very slow speed, is actually indicated somewhere in between 7 to 15 miles an hour, and it's operating in an adjacent lane to an active roadway, which in some cases could be going at speeds of 70 miles an hour. And when the TMA truck is impacted, in worst case, at 70 miles an hour by an 80,000-pound tanker truck, the person driving the TMA is exposed to extreme risk of danger and serious injuries and rehabilitation. It's really a bad situation. So that was our motivation for expanding our product line into the commercial space, and in understanding that we had this application of the technology to increase safety. So we went down this path in about 2014, and we put together a baseline system, and we teamed up with a company in Pennsylvania called Royal Truck and Equipment, and they are the nation's largest upfitter of highway safety and maintenance vehicles. So they provided some vehicles. We did a baseline demonstration. Shortly after, Colorado Department of Transportation got involved, and they really did a great job in helping us understand the actual operations that the TMA truck is used in, and they did a great job in helping us integrate the features and capabilities of the system to tightly align it to this application of highway maintenance. So what we have today is a very mature autonomous maintenance vehicle that has a significant amount of miles and significant amount of input from departments of transportation across the United States, to also include some collaborators we have overseas who also deploy truck-mounted attenuators, or in some cases they call it an impact protection vehicle. So just gives you a little background on what the TMA is and how we got involved in this project, and why, what the overarching goals are for us in increasing safety for the work zone. As I indicated, these vehicles are deployed in all 50 states. They're deployed day and night in a variety of maintenance applications. Why we automate this truck, I think it's pretty obvious. Here's an example of why we do it. When these trucks are impacted by heavy vehicles, it is very dangerous for the driver of the TMA. As you can see in the picture there, the TMA is often pretty well destroyed in some instances. And looking at some of the statistics across the United States, we're seeing that there can be over 90 crash-related injuries and 11 fatalities every week in the work zone. And this is a significant motivator for us, and why we want to get this right, and why it's important to have these vehicles deployed in the autonomous configuration. And one thing to take into consideration here is when we automate the TMA truck, it's a great opportunity for the person who used to drive the TMA. So this person is now removed from the TMA truck as a rider, as a driver, and they're transitioned to another vehicle ahead in the work zone in a much safer location, and they have a user interface that allows them or enables them to monitor the unmanned vehicle. So with this project, we've actually developed a great strategic workforce development opportunity for the truck drivers, which has been very helpful in garnering interest in highway maintenance. A lot of the younger people that we need to support these work tasks and maintain our critical infrastructure are not really all that interested in being in the environment. So now with this opportunity to work with driverless vehicles, it's really been great in helping the recruitment efforts in garnering younger and new talent to the industry. So some more crash statistics that we've seen in the United States. As I mentioned, we've got 90 crash-related injuries daily, 11 crash-related fatalities weekly, and over 710 crash-related fatalities in 2017. We use 2017 because that's the data that we had, the most current data that we had for the space. In the UK, we put some data over there for the UK. There are 741 crash-related fatalities in 2017. We do have an autonomous vehicle that has been deployed in the UK, so we track some of the data there as well. So there's a lot of interesting data. When we first started getting involved in this arena and looking at the industry overall and the interest in whether or not an autonomous vehicle could be used or could be deployed, there was not a lot of data that we could find on crash statistics specifically related to TMA trucks. So another great side benefit to the project is now we're seeing a lot of DOTs actually collecting this data, which is being used for justification for acquiring and evaluating and investigating the use cases of deploying driverless TMA trucks and other maintenance vehicles. So it's really been a great overall accomplishment with the project. So what I wanted to present here is this was testimony that was provided by an actual TMA truck accident survivor. Mr. Katz was providing testimony when for Pennsylvania congressional hearings where they were drafting legislation to allow for driverless maintenance vehicles to be put on the road. So Pennsylvania didn't previously have legislation in place. However, we've done a lot of work with Pennsylvania state government, the DOT, the tollway, and they recognized very early on the importance of the autonomous truck-mounted attenuator, and they had a strong desire to get the vehicles on the road in Pennsylvania. So first step for them was getting legislation in place. We supported the legislative hearings for the bills that were drafted out, and Mr. Katz provided testimony, which I can provide a link to this video. It's fairly long, but He really gave some great testimony of what it's like to be in the vehicle and be in an accident. He was actually in 2 accidents himself. One of the accidents, he had a colleague in there that was very seriously injured. Mr. Katz as well was seriously injured, and he's still recovering from some of the injuries and really the experience overall. But one of the things that he stated in the hearing, which I thought was very important, was his recognition of the system, in that this is going to save lives. This is going to prevent any of us to have to come back here and talk about how we almost died and how we could have not seen our kids, which is obviously very powerful, and it really encompasses the reasoning for the system and the why of why to deploy this autonomous technology in this way. So just to talk a little bit about how the technology works, Ashley gave a really good description in her presentation, to just kind of hit a little bit more. Whoops. The system is deployed in a multi-vehicle convoy. So you have 2 vehicles. One is the lead vehicle, which is usually a work zone vehicle, and there is kit that is installed in that vehicle. And then obviously there is the follower vehicle, which in this case is the TMA, and we install kit in that vehicle as well. So the kit that we install in both vehicles consists of a computer, a navigation system, communication systems, and some user interfaces. In addition to that, we also install in the driverless follower vehicle, the ATMA, actuators to control steering, braking, and throttle, and then also sensors to monitor the environment and provide situational awareness for things like, obstacle detection, obstacle awareness. And so essentially, as the lead vehicle is human driven, it's driven down along its route. Navigation data is collected and transmitted at 10 times per second to the follower vehicle, and the follower vehicle simply translates that navigation data into its path and simply follows the leader. So wherever the lead vehicle goes, the follower will follow. And the system operator uses a user interface, which is a graphical user interface to a computer touchscreen. They have a status on the display. They have video where they can see the driverless vehicle behind them. They have status of the navigation system, status of the communication system. They also see status on obstacle detection and other safety features. And they are able to control the vehicle-to-vehicle gap. They can extend the gap from about 50 feet to about 1,600 feet as needed, so they can do that on the fly. They can stop and pause the vehicle. They can also do a left-right lateral offset, so they can offset the TMA from the lead vehicle by about 12 feet plus or minus, so it's 12 feet to the left or 12 feet to the right. And so they have a lot of control over the overall system. And as I mentioned, they can stop the vehicle at any time in various levels of stopping, depending on what the reasoning is. And there's also an independent safety system that operates that in case the computers all lose their brain, a person in the lead vehicle still has the ability over the independent wireless communication system to stop the TMA. Okay, so the system itself is very self-contained in that we only have some very minor interfaces to the actual truck itself or to the vehicle. So we're not interfacing the J1939 CAN bus. We're not interfacing to the vehicle's onboard computer. We provide all the equipment in the vehicles that's needed to automate the vehicle. And we do this for a lot of reasons. Number one is, we want to cyber harden the system. So we want to limit the access points to the system. So we're not using any Wi-Fi or Bluetooth. The only communication system that we have is the vehicle-to-vehicle communication system, and that's a redundant system, meaning there's two simultaneous systems, 2 communication systems operating simultaneously, one on one frequency and one on the other. This communication system is hardened with AES, which is a military-grade encryption. And then we also have integrated in there a frequency hopping capability where the communications links is jumping between various frequencies continuously as it's in operation. So we do all this stuff to harden the system against cyber attacks and malicious hacking. As I mentioned, there are a number of active safety systems in operation. So we're monitoring the different computers and the different electronic systems for any kind of faults. And the default The default operation, if there's any fault detected, is to stop the ATMA, okay? And there's various troubleshooting and status indicators that the system operator can look at and review in an effort to maintain the properly operating system while it is deployed. And again, it's worth noting that this person who is the system operator was the person that used to be the TMA truck driver. So we had this opportunity to maintain the workers' function in that they're still being deployed with the work zone. However, their tasking is quite a bit different from what their original tasking was. And these folks are trained to use the system, whether they're using the system operator, system operation display, or even if they're the leader truck driver. So we put together a pretty extensive training suite to make sure that everybody operating the system is comfortable with it as they're deploying in their normal highway maintenance operations. So this picture shows a little bit of the system, some of the internal components. As you can see in the top left, the steering actuator that we add to the vehicle. The steering actuator essentially fits around the steering column, and it's kind of hard to see from this picture, but there are two fingers that connect or interface to the spokes of the steering wheel, and they essentially enable left-right steering of the steering wheel. These fingers can be left in while driving the vehicle in manual mode. However, they're just it's just a thumb screw to hold them in place, so you can remove them. And it's also important to note that the vehicle can be operated in manual or automated mode with just the flip of a switch and removing these fingers here for the steering actuator. So it's important because it enables you to dual use the vehicle such that you don't have to dedicate it necessarily to the specific ATMA program or operation. Some of the folks that have the system deployed actually use the TMAs in the summer as TMAs, but then in the winter they dual purpose it as a snowplow vehicle. So they remove some of the components and use it in that capacity. Below the steering actuator, you see the obstacle detection system. This is a detect and avoid. This is a redundant system. It uses a 2D LiDAR sensor, which you see on top. And below that, there is a Delphi ESR radar, which is used. We use multiple sensors because they have advantages in different operating environments. Some work better in rain and snow, and others work better in detecting plastic obstacles like cones and things like that. In some cases, for example, the radar will see right through a plastic cone, but the LiDAR will pick it up. So we wanted to make sure the system was as robust as possible, and obstacle detection is a very important thing. Obviously, we've spent a significant amount of time in fine-tuning and honing the control algorithms for the obstacle detection system, and creating a very robust solution that enables the vehicles to operate in the very complex work zone environment where there's typically a lot of equipment and cones and people and different operational scenarios that need to be supported. So the idea is we want to limit as much as possible false positives on the obstacle detect system because it could be very annoying if the vehicle stops all the time. However, we wanted to ensure also that the system is going to pick up the variety of different obstacles that can be presented. Anything from between a child or a small pet to a human or some kind of equipment. Also, what you can see to the right of that shows the user interface. There's three monitors that are stacked up to the left. That's not part of our system. That's part of the other equipment that's actually installed in the vehicle for systems unrelated to the autonomous. Our system is the single display to the right of the triple stack display, and the yellow and red buttons. Those buttons, one is the normal A-stop interface, which allows this person in the lead vehicle to stop the ATMA. And the red one is the independent e-stop, and either one of those buttons could be engaged to stop the TMA at any time. Also external to the vehicle is that big red e-stop safety button, so that if somebody outside of the TMA in the work zone needs to stop the vehicle, they can also walk up to the vehicle and stop it for any reason. And so all these systems are retrofit into the vehicle, right? The idea is that we have developed a truck agnostic solution. So whatever trucks and fleet vehicles the DOTs already have in play, we can integrate the kit on them. And all we need to do is design in the installation kit, which is the vehicle-specific brackets and some vehicle interfaces, like, for example, controlling the blinkers and things like that. So there's your vehicle specific aspect to the installation, and then of course the kit components, the computer, nav system, sensors, and all that sort of stuff is the same across all the different platforms we've deployed. Oops. All right. So to date, we have deployed 10 systems across the United States. We have and also one in England. We deployed the one in England that was the first one. Shortly behind that, which was almost in the same week, we deployed the one in Colorado. We now have 2 systems in Colorado, one in the Greeley area, one in the southern Durango, Alamosa area. We have 2 systems now in Missouri. One is in the Kansas City location, and one is just been deployed in Springfield. We've got a system deployed in California with Caltrans. They've spent the last year validating the system and doing various tests and verifications. The system has now been approved and will be deployed in live highway maintenance operations in September, October in the San Diego area. So it's a big milestone. I think the plan there is to deploy for 6 months with a safety rider in the driverless ATMA, and then 6 months with the vehicle completely unmanned. So fully vetting the system for California operations. We also now have a system in Minnesota as well as a system in North Dakota in various levels of their initial deployments. We've also done deployments in Tennessee, Florida, and we have a deployment on deck for Indiana with Indiana DOT and Purdue for this summer. So we'll be doing some specific applications there. You can see from the chart that some of the TMAs have actually been purchased by the DOTs. Others, like Tennessee, Indiana, and Florida, have leased the TMAs for to do their evaluations, and working with those DOTs and their different operational scenarios and pending purchases here in the future for getting the vehicle on the road in a more permanent operation. So as I mentioned, we put more than 2,000 miles of operation, probably a little bit more than that even by now, but since 2017, we've talked about the different locations that we're at. There's also a pooled fund in play, which has been a great networking forum for discussion. It's really been an important component to the development of the TMA and getting feedback from all the different DOTs. One of the most important things and one of the greatest things we found with being able to deploy TMAs in all the different locations is everybody does maintenance operations a little differently. So we've been getting great feedback on different features and functions, and it's all played into developing this very robust system that we are at a stage right now where the system is pretty accommodating to the majority of maintenance functions across the United States. A great example is when we did our deployment in Minnesota. They do some things with shouldering where they really needed to have an offset feature where they can offset the TMA, operate the leader vehicle on the shoulder and the TMA in the lane. So that was a new feature. Came from those folks that we were able to integrate into the system, and now it's rolled out across all the different states. So a lot of things like that came out of Colorado and Missouri and the different locations where we've been deployed. So the point is, it's really important that we get a lot of eyes on the system and opportunities to deploy in all different locations, so we can put together the most usable and least work impeding system for operation. So we got a lot of good feedback, as I mentioned, on the TMA. I put together some testimonials, which I always like to have. It just kind of gives folks a good feel for the system and great for creating public awareness and that the work that we're doing is appreciated. And that's work not only Kratos is doing, but also the DOTs who are participating on these programs. So, just Colorado has been a part of the program since the beginning, and they've had a lot of experience on it. North Dakota DOT is one, has had their system since, I think, at the end of 2019. So they've had a lot of good feedback with the system. They're deploying it in their different operations currently, and we're continuing to support all the different DOTs that do have the deployed systems. And we field different questions. We support follow-on training as needed when new folks are brought into onto the programs or into the maintenance operations where the ATMA is used. And we also support, any kind of maintenance and sustainment requirements for the vehicles, and we put together in collaboration with the DOT these sort of programs to help maintain safe operation and continued operation of the system in achieving its goal of increasing worker safety. So I always like to show the notable awards. It's always exciting to think about, how we just basically came up with an idea for how technology developed for the military could be applied in the commercial world, and receiving some of these awards from industry related agencies and third-party organizations, recognizing the important work that we've done. It's really a great feeling to know that we've stumbled upon a technology that's had a big impact in the maintenance arena, and we're positive towards the future that we're going to see more and more interest and continued use and expanded use of the ATMA and other maintenance technologies, automated maintenance technologies that we have on deck for development. So a few of the primary benefits for the ATMA with regard to driverless technology. Mainly, the big takeaways I think for the system are that make the ATMA a great icebreaker autonomous vehicle for different states is that, number one, it operates in a very controlled environment. Number two, it operates at relatively slow speed, so anywhere between 7 to 15 miles an hour. And number three, which is most important, is the primary objective is safety. It's not about mobility, it's not about moving freight, it's not about enhancing efficiencies and anything like that. It is literally about increasing safety in the work zone. There's a very clearly defined objective for the system, and what we found is it's the users appreciate the easy to use deployment of it, and that's a big reason for how and why it's been successful. And with that, I'll open up for any questions and transition to the next presenter.
Thank you, Maynard. We will save all the questions to the very end. Could you stop sharing so the third presenter can start? Yeah, Tim, feel free to take it over.
Okay, sure.
Yeah, we can see your screen, Tim.
Okay. Hello, everyone. The title of my presentation is Development of Operation Guidelines for Leader-Follower Autonomous Maintenance Vehicles at Work Zone Locations. As we are familiar with the ATMA vehicles, including one leader vehicle and one follower vehicle. So this special leader-follower system design imposes more requirements on the leader vehicle drivers. So this work aims to develop some operation guidelines for drivers to ensure a safe and smooth system operation. The leader vehicle driver is required to make driving decisions not only from their own perspective, but also to consider the follower vehicle. For example, when vehicles are making lane change, a regular passenger vehicle driver can simply find an acceptable gap in the traffic flow and change the lane. However, the leader vehicle driver will have to wait for a gap larger than normal for both vehicles make a lane change. So we needed to determine what are the minimum requirements, especially in some critical decision-making locations: the car following distance, lane changing gap, and intersection clearance time. First, I would like to introduce how to analytically derive the car following distance and an acceptable gap for lane changing for a general vehicle. For the car following distance, we adopt the New Well's simplified car following model. And the first figure here shows the time space diagram in which a leader vehicle N-1 travel at the speed V1 at first, and then it changed the speed to V2. And here we can see the following vehicle N also travel at the speed V1 and then change to V2 at a turning point with a spatial delay Dn and a temporary delay tau n. So according to the new wheels car following model, we can describe the following vehicle's trajectory xn of t plus tau n equals to the xn minus 1 of t minus the spatial delay dn. So here we can clarify that the required car following distance Sn equals to this spatial delay dn at the velocity multiplied by the tau n. So the second relationship between this spacing and the velocity for a single vehicle. About the critical gap for lane changing, we adopted a lane changing model proposed by Young in 1996. In their model, an acceptable gap in 19 and include a leader gap, leg gap, and vehicle length, and plus the vehicle length. Typical scenario, there are two lanes in one direction, and we assume that this subjective vehicle intended to change the lane to the left lane. So according to their model, the acceptable gap equals to the leader gap between the leader vehicle on the target lane and the subjective vehicle, and plus the leg gap distance between the leg vehicle on the target lane between the subjective vehicle and plus the vehicle length. And those gap distances are determined by the speed and the acceleration. Before proposing the model, another important concept, roll ahead distance, needs to be considered. In the work zone, a truck-mounted attenuate-equipped vehicle should be positioned as a sufficient distance in advance of the workers or equipped being protected. And the roll ahead distance varies depending on the width and speed of the two vehicles involved, and also the extent to which the shadow vehicles is restrained and certain pavement characteristics. And recommended by the AASHTO, if the shadow vehicle's weight is greater than 22,000 pounds, and for different traffic operating speed, and the roll ahead distance is recommended by 100 feet to 172 feet. The data was collected from a field testing, and the first table is showing the data connected from the leader vehicle, including the time information and also the position information, including the latitude, longitude, and altitude, also the heading and the velocity. And for the fuller vehicle, we are connecting more information. Apart from the above information, there are the desired heading distance and gap distance, and also the cross-track error and the acceleration. And here the cross-track error means the latitude or longitudinal deviation from the intended path or the leader vehicle's path. To estimate the car following distance and the lane changing gap, we need to clarify the deceleration of ATMA vehicles. And this table shows the stop time and the stop distance in emergency stop test. So when the operation speed is 10 miles per hour, the average deceleration is 9.1 feet per second squared. And when the operation speed is 50 miles per hour, the average deceleration is 11.4. And we use the braking reaction time, 2.5 seconds recommended by AASHTO. According to new wheels car following model, the minimum car following distance for a leader vehicle equals to the speed of the leader vehicle multiplied by the reaction time and plus the braking distance. And this figure shows the results of the relationship between the operating speed of the ATMA vehicles and the minimum car following distance. So as the speed increase, the minimum car following distance also increase. So the minimum car following distance is suggested to be set as 75 feet. For the fuller vehicle, since it drives autonomously, there is no reaction time, and the minimum car falling distance only includes the braking distance DFT. However, we needed to consider the system error in falling distance, and this figure shows the error distribution in falling distance. And we take the 95 percentiles 6 feet as the value of the system error epsilon. And we can find that this item is less or equal to 26 feet. And in addition, as mentioned before, the roll ahead distance also needs to be considered. So we can derive that the minimum car falling distance for the follow vehicle equals to the roll ahead distance, ranging from 100 feet to 172 feet, according to different operating speed. And the lane changing decision-making process of ATMA vehicles is different from the general vehicles, since it includes 2 vehicles. And in this typical scenario, in the ATMA vehicles would like to make a lane changing to the left lane. So the minimum acceptable gap distance includes 3 items. The first one is the leader gap distance between the leader vehicle and the leader truck and the leader vehicle on the target lane. And the second is the lag gap distance between the lag vehicle on the target lane and the follower truck. And the third item is the gap distance between these 2 vehicles and plus the ATMA vehicle's length. And to evaluate the critical lane changing gap, we brought the critical or minimum time headway. Since to avoid the crash, the critical time headway relies on the response time of the driver and plus the stopping time equals to the speed divided by the acceleration. So for the first leader gap distance, the minimum time headway equals to the response time for the leader vehicle's driver's response time plus the stopping time. And for the lag gap distance, the minimum time headway equals to the response time of the general vehicle and plus the stopping time. Here the VFS means the free flow speed for general vehicles. And the A of GV means the acceleration of the general vehicles. And for the gap distance, since there is no reaction time, so the minimum time headway equals to the distance between the 2 vehicles and divided by the speed of the ATMA vehicles. And these 4 figures shows the critical time headway and the gap distance required for lane changing. And the first 2 figures means that the gap distance between 2 vehicles are said to be 100 feet. And these 2 figures means that the gap distance between 2 vehicles is said to be 200 feet. And we also shows if the operating speed for the general vehicle's speed is 35 miles per hour, 50 miles per hour, or 70 miles per hour. So for the typical scenario, if the free flow speed is 70 miles per hour and the gap distance is said to be 100 feet, the critical gap distance for the ATMA vehicles range from 886 feet to 940 feet, and time headway is 25 seconds to 47 seconds. At the intersection, the clearance time requirement for going straight equals to the intersection length and plus the gap distance between 2 vehicles and the 2 vehicles' lengths divided by the speed. And for the left turn, the time for make a left turn equals to the intersection wise and plus the gap distance between 2 vehicles and divided by the speed of the ATMA vehicles. And we can find that the clearance time for making a left turn or go straight, they are ranging similarly. So the required time for gap distance 100 feet, the clearance time is ranged from 10 seconds to 31 seconds as the operation speed of ATMA vehicles increasing from 5 miles per hour to 15 miles per hour. And if the gap distance is set to be 200 feet, the clearance time ranges from 15 seconds to 45 seconds. Those guidelines can be applied by combining the CV technologies, as we know the ATMA vehicles are equipped with many sensors, radar, LiDAR, or camera to detect the obstacles and their distance between around the vehicles. It can also apply the vehicle to infrastructure communication, to receiving the information from the traffic signal controller before approaching the intersection. For example, for when the traffic light is green, the driver needs to know how much green time is left and whether it is enough for 2 vehicles go through or make a left turn. And that's all of my presentation. Any questions and comments are welcome. Thank you. And this work has been published in the journal, so you can get more detail from this paper. Thank you.
Thank you so much, Qing. So now, okay, so now it's a Q&A time. We have received quite a few questions. I will read them out one by one. The first question is to Maynard from Kratos. Maynard, the first question is, what is the sensor used for obstacle detection? Are you using LiDAR or something else?
Oh, we're using a combination of 2D scanning LiDAR and electronic scanning radar. So the Delphi radars, which are pretty standard on most vehicles today.
Okay, thank you. And the second question is for Ashley. Ashley, the question is, have you tested what happens to the ATMA vehicle if it is hit? Does it automatically stop?
Thanks, XP. That is a good question. We have not tested that, but it's actually very timely in that our pooled fund members recently awarded a research project that will happen down in Texas that will test at a slow speed what happens to the ATMA, how it responds when it is struck. We certainly have what we would expect to happen from the performance specifications of the vehicle, and we will test that that's actually what occurs in reality come this fall. So please stay tuned.
Okay, thank you, Ashley. Great to know the pool fund is already tackling this important question. And the third question is again for Maynard. Maynard, the question is remote controlled locomotive operators. They have to wear a control pack. Either it's a belt mounted or suspended from the operator's neck. Does your vehicle controller have to wear any types of controller pack? And if so, are they equipped with the tilt sensor to shut down the vehicle if the operator is not standing upright?
Okay, so our system has remote control capability in that a system operator can adjust gap distance between the vehicles or left-right offset and then monitor and then perform system monitoring. However, they are not physically controlling the vehicle. They are not making the vehicle go forward. They're not turning the vehicle. They're not controlling any part of the baseline mobility of the vehicle. So they don't need it. It's not required for them to have some sort of control panel. And I know what they're talking about, but it's not required for them to have a control panel attached to them that enables them to control the vehicle. They are located in a control room environment, if you will. In most cases, it's in this vehicle that has the leader kit. In some cases, they ride in the passenger seat of the vehicle with the user interface mounted to the dashboard right in front of them. and there's a touch screen display that allows them to adjust gap and alignment and monitor the performance of the system. In striping operations like we have in Colorado, the user interface is, at least for now, it's mounted in what's called the doghouse, which is where the operators sit to control the painting mechanisms for striping the road. So they have a person that sits in there with those folks that are operating the paint equipment that monitors the system. So the answer to the question is no. There is no system or control panel that is attached to a system operator. The system just doesn't work in that capacity. The control data, the navigation data is literally transmitted from the leader vehicle to the follower, and the control algorithms are translated from the navigation data that is transmitted to the follower vehicle. So as the human being is driving the lead vehicle, this navigation data, which is basically speed, heading, position, and whatnot, is packeted and transmitted to the vehicle. So that's how that works.
Okay, thank you, Maynard. Hopefully that answers the question. If not, feel free to follow up so that and then I can read them out again later. Actually, the next question is for you. I see you provided answers already, but let me read it again. Just in case needed, do drivers have any difficulties backing to the ATMA vehicles?
Hi, XP, thanks. I think I asked for a little bit of clarity. I assume that the question was regarding reversing of the lead vehicle. If that's not right, please, I'd like the audience member to clarify so we answer the question correctly. But we actually, in our operational design domain, we do not have any need to do a reverse operation. We haven't tested that since it's not in our ODD that we have on file with the task force. And I would actually pitch it over to Maynard on any testing, Maynard, that you've all done, or if there's capability to do that reverse operation.
Yeah, for operating the vehicle in reverse, no, that is not a feature that's been added to the system. The way the system works is leader follower. So we need the vehicle in the front to guide the follower vehicle. If the lead vehicle is going in reverse, there's just the path for the follower vehicle is not accurate. So it's not something that we've done at this stage in the game.
Okay, thank you both. The next question is to Maynard. The question is, who is responsible to install the kits? And do you have a bulk part of the cost? How much are we talking about? And also, do you have any data to show the system reliability, for example, the system downtime? And also, I will let you answer the first portion first, Maynard, and then I proceed to the second portion.
Okay, so the first part of the question was who's responsible for the kits?
Yes.
Okay, so Kratos produces the kits and delivers them. We also install them in the vehicles, and once the kit is installed in the vehicles and the system is deployed with the end user, the DOT or whomever the user is, we then we work with them to figure out the maintenance sustainment plan. So it could be a maintenance contract for Kratos to maintenance the system. We can train the end user to maintenance the system themselves to the unit level, meaning can they if there's wear and tear on the system, we can provide spares and deliver the spares, and the end user can install them with training. And so there's a variety of different aspects in how we can support that, and we're supporting that in different levels with different customers that are currently using the ATMA. And we expect to have as we continue forward and we deploy more and more, we expect this function to grow and probably at some point get more formalized in an arrangement, either just whatever works best, whether it's the end user maintaining, supporting the equipment, whether it's Kratos, or whether we bring in a third-party small business to do something of that nature. What was the second part of that question?
It's about the cost of the system
Cost.
and also the system reliability.
Yeah. Okay. So cost is a number that has a lot of components tied into it. You know, is there training involved? Is there deployment support involved? Have the kits been installed on an exact year and model of vehicle previously? As I mentioned in part of my presentation, there is a development effort, if you will, to design the installation kit per the specific vehicle. Not all vehicles are the same, and where actuators are mounted and what brackets are designed and how cables are run and all that kind of thing is somewhat vehicle specific. So if we've developed an installation kit for that particular model of vehicle, obviously that component is not needed. But just to kind of give you a ballpark, the average price for System 1, which is the very first time a system has been integrated at a DOT, and it includes some training, it includes some deployment support. It's usually in that 350 to 300K ballpark for the entire leader follower system installed on the trucks. And this is very low quantity. This is one piece quantities. We're starting to see more and more systems being purchased, so the pricing is going down. Also, we have a new version of the system that will be coming out soon, which is a more consolidated system, which we see is going to be another cost reduction component to the system. So that's kind of where we're at. I'm estimating follow-on systems, in various quantities are going to be ranging anywhere between 100 to 150,000 for the full-on systems, and then of course all the extras could be added to include, if it's a new truck or how many trucks are being installed on, if there's training components required and deployment support, which those components require some on-site travel. So that all plays into the cost. And I usually I'm pretty good at working with the customers and figuring out the best path forward for them in as far as initial deployment, the most bang for the buck, and then follow-on deployments from there.
Thank you, Maynard. Another question is also for you. If DOT purchase the system, do they need to upgrade either the hardware or software down the line? And what is anticipated product life?
Yeah, so in the early days, 2017 timeframe, when we first started getting the system on the road, there were a lot of hardware and software updates. The system was in a very baseline configuration. It was essentially a defense contractor designing a system to be used in an industry that we were not the experts in. So the DOTs were very helpful in helping guide the design and figuring out what features and functions and system components were needed to be a safe and reliable deployment. So in those days, we were doing a lot of pretty much no cost upgrades, because it was beneficial to everyone overall. It helped us design a robust system, and it helps the users have a system that they want to use. And moving forward, if we find use cases that may require a software update, and it's not a significant update, we're pretty open to doing that at no cost, especially if it's something related to a safety case, or if it's just maybe a bug that's happened to be identified in an unusual operation. An example would be we just did an upgrade for very slow moving operations where the vehicle is moving at speeds less than 3 miles an hour, so somewhere in that 2 mile an hour range. And there's a lot of reasons why things need to be upgraded. But anyway, so we did that upgrade. It was a hardware and a software upgrade. So we did the software upgrade at no cost, and we had some hardware that needed to be added. But moving forward, it's going to be kind of a case by case basis with regards to pricing of upgrades, right? And obviously we're gonna prioritize as much as possible, say anything safety related that are identified, or any features that look like they are very applicable to the masses, like something that somebody identified that maybe everybody would like to have this upgrade. We would consider things like that. So I'll just kind of leave it at that. You know, we're working with the folks that have the deployments right now, and we consider them great collaborators and teaming partners. So we obviously want to make sure that they have the best product on the road, and when there's an opportunity to do an upgrade. And you know, I mean, we are in business, and I do have to keep the lights on. So in some cases, I do have to charge, but we try to best accommodate the customer in a lot of these cases. The lifespan on the system, you know, we're estimating at least a 5-year lifespan on the system. We want to be able to at least maintain or at least operate for the usual lifespan that the trucks themselves are used. If we get brand new trucks, you know, that could be extended. If we're getting older trucks, you know, maybe we have a couple of years on one model of truck, and then we could take the kit and install it on a new truck. The kit itself, I mean, for the most part, it's electronics, so they can move from vehicle to vehicle. The actuators are very high reliability, industrial grade, military grade actually actuators. We don't make them in house; we buy them, and these have a very high mean time between failure. So you know, there's a significant life cycle beyond the system, and so it makes sense, you know, if you're doing a cost comparison or an estimate for deploying on a truck and what you're going to get out of it.
Thank you, Maynard. The next question is for Ashley. Actually, the question is on the operating conditions, especially during the extreme weathers, like extremely hot, extremely cold. How does the vehicle perform?
Thanks, XB. In my response, I did note, you know, generally, since our use case is focused on paint striping, that use case requires fairly optimal weather conditions in general. So in general, you know, we're operating when the pavement is dry, it's 50 or 60 degrees at the pavement level. So we're typically not operating in sort of those extreme cold, certainly those wet sort of ODDs. We certainly could, and I think that's something that we are willing to evaluate from a performance aspect and safety aspect. But right now, it's just not really an issue when it comes to our particular use case. But I would, again, throw that over to Maynard. Maynard, if you have, you know, more details that you can provide on the performance of the system in some of those inclement weather conditions.
Yeah, thank you, Ashley. So yeah, at this stage in the game, the system is been designed for mostly, you know, fair weather and fair weather conditions. However, it has been used in rain conditions, and essentially we try to design it in as best as possible in the environment that a human would operate. So heavy rain, it's been used in some occasions, and it's worked out pretty well. We are now hardening the system. We have some other programs that are going to be in the frozen north, North Dakotas and Minnesotas and locations like that. So we are hardening the systems. In some cases, you know, like the sensor systems, for example, have other versions that have heaters and different things in there to maintain operation in harsh winter environments. So we're looking at like a winterization kit if the system needs to be operated in the cold weather environment. And then there's some other things with control algorithms that we're looking at to enable operation on icy roads and snow and that kind of thing. So that's a near-term feature enhancement that we're going to be deploying here, likely before the end of the year. So we'll have some winter operation features on the system by then.
Thank you both. The next question is again to you both. The question is, what is the smallest object that this vehicle, what is the smallest object this equipment can detect before it stops in terms of the dimension? So maybe Ashley, start from you.
Yeah, thanks, XB. We've done, as I mentioned, we've done quite a bit of testing, particularly around the obstacle detection components. And Maynard did highlight, our two different vehicles do have two different obstacle detection inputs. So one has the LiDAR based system and the other has more the ultrasonic based system. So we've tested, fairly extensively, I would say, what the detection is like for both of those different types of technology. Without getting into too much technical detail, which I'll leave for Maynard, I will say,
during our tests, many times, the obstacle detection has actually stopped the vehicle when something like a tumbleweed has flown in between the vehicles. So it's fairly impressive how granular that obstacle detection can be. Certainly you do need to be aware of what are the technology specifications with sort of the radar detection cone and those sort of traditional aspects of an automated driving system input. But at sort of a basic level, we have been very impressed with the obstacle detection's ability to detect surrounding objects. It goes without saying, it has, of course, will detect when a human is on the side. I think Maynard highlighted that in the user interface that our safety operator is using, that information is actually displayed on the screen. So the safety operator knows that an obstacle has been detected. It details where the detection is at. Everything sort of under that umbrella is provided, that information I should say is provided to the safety operator. But Maynard, I'll pass it over to you again to give more sort of the technical detail.
Yeah, so we've spent a lot of time, like I said, in the obstacle detection world and honing the control algorithms for that, and you walk a fine line between detecting every single thing and false positives, right? And an example of false positives, in some cases where we've been demonstrating on abandoned runways, airstrips, or whatever, doing some kind of baseline testing or initial testing. We've picked up little tufts of grass that are sticking up in the road, So and we actually did a lot of work in the UK with their system on this. And they had some interesting operating environments. They operated on very narrow roads, and in a lot of cases they had cones on both sides of the truck. I mean, inches from the side of the truck, and they would operate in chicanes, which is like a cone lane that then angles left or right, and the vehicle has to be able to drive through this cone lane to perform its work. And we would have situations where we would be picking up all the little cones and all this kind of stuff. So what we have in place right now is a very robust system that simultaneously looks at the 2D LiDAR and the radar. And the 2D LiDAR allows us to detect certain things. Like I mentioned earlier, cones are sometimes invisible to the radar because it just sees right through them. So the LiDAR is needed for that capacity. And we went with a 2D LiDAR. We have a 2D LiDAR incorporated now, which previously we used to have a 1D LiDAR, which is more like a rangefinder, but it just wasn't robust enough. It just didn't give us the fidelity enough to determine what was maybe a cone and what was maybe, a speed bump or a piece of grass, right? So the 2D LiDAR gives us that more robust capability to differentiate different things, and it's what enables us to operate in very complex environments. And like I said, we use the radar and the LiDAR at the same time, and there's algorithms in there that are sort of comparing notes between what the two sensors are seeing, and that's what enables us to detect fairly small objects. I mean, I don't know that we've done specifically any testing that said, okay, what's the smallest we can get starting from a marble and going up to a beach ball. But we've done a lot of tests where a person might be crouching, bicycles and scooters and things like that, getting in front of the vehicle at different speeds. Also, I've walked in front of the vehicle many times, and I'm still here to talk about it, so that's good. And yeah, so I'm not saying we have the most we have an airtight, never to be breached obstacle detection method, but it is better than most. I could comfortably say that. And if you look at other systems that are deployed, operating in a work zone or operating near a work zone with an autonomous vehicle is a very challenging thing. So to be where we are and be acceptable for use and not annoying in that the vehicle stops every moment, it says a lot for the work that's gone into developing that obstacle detection system.
Okay. Maynard, this is the final question to you. Please be quick because we're running out of time. The final question is about system upgrade. When a DOT purchases a system, does the system upgrade requires us to replace the entire system, or is it a certain component or software based? Please be short. Thank you.
Sure. It's very rare that we have to replace the entire system. Even starting from day one, when we deployed the first system, it's usually a software upgrade, or it's a box that is added. So,
Okay. Thank you, Maynard. Yeah. We're running out of time. Back to you, Deanna.
Okay, well, thank you, XB, Ashley, Maynard, and Ching for the presentations and discussions. I would also like to thank the audience for joining us and participating today. When you sign out of this session, we encourage you to take a brief evaluation regarding your experience. We use these evaluations to improve our webinar program, so your feedback is greatly appreciated. And lastly, please make sure you are subscribed to TRB's weekly newsletter. Have a great afternoon, and we hope that you can join us again for future TRB webinars.